which we kind of look, we can basically compare different. All right, let's put it this way. All right, so far we have looked at different characteristics of real-world graphs. Now, what we want to do, we want to construct algorithms to generate graphs that show these characteristics. For that, before going to deep generative model, what we want to look at is the traditional approaches with which, before even machine learning or any deep learning, people generated graphs to study network science essentially. And then we use elements of these approaches in order to build our deep generative models. So the idea is simple. We want to construct non-trivial graphs that represent real-world, essentially, networks. And then this, basically different approaches are characterized by a generative process. So means that the process with which we construct this graph. There are four approaches that we're going to look today. The first one is Shervani-Tabar, or the random graph model. The second one is configuration model that we'll look briefly in our basically node importance measures, LHN model. Then there's stochastic block model. And lastly, we're going to look at the Barbara-Shelburne model. So, starting from Shervani-Tabar, this, as I said, is also known as random graph model. This is the most well-known model to generate graphs. And then the idea behind this approach is that we just assume that we are giving a number of nodes, and then the edges just randomly connect these nodes together. So essentially, edges are randomly placed throughout the graph. Now, what that means is that I'm assuming that there is a constant probability that with which we select if there is an edge between a given pair of nodes or if there is no edges between them. So mathematically put, it means that the probability of having an edge between nodes Vi and Vj is given by parameter R. So for any two given nodes in the set of nodes in the graph, without any self loops, we just select a random number. If it's larger than R, we have an edge between those two. If it's smaller than R, we don't have any edges between those two. That's the essence of the generation of the graphs using Shervani. So just to basically put that in notes, let's say that we are given V nodes. So we know that we are going to generate a graph with V nodes. And then we're going to select any pair of nodes in that graph. One by one, we're going to go through all pairs of nodes Vi and Vj. And then we're going to sample a random value, R prime, between 0 and 1 uniformly. So if this R prime, and you're given some parameter R that shows the probability if there is an edge between two nodes in this graph. So this R prime, if it's larger than R, we're going to connect these two nodes, Vi and Vj, and so that's going to give the probability R to having the edge in that graph. Otherwise, there is no edges between those two. For instance, here we have 7 nodes. You're given the probability of 5 for having edges in this graph, and then you're going to select, for instance, these two pair of nodes, and we're going to sample a random number. Let's say that the sample number, the random number that we got is 0.2. So it's smaller than 0.5. So there's not going to be an edge connecting these two. We move forward to the next pair. We see that the random number that we sampled is 0.7, larger than 0.5. So we're going to have an edge connecting these two. And we're going to continue that until we are done with all the pairs of edges in this graph. So we have one parameter in this model, and this parameter is controlling the density of the graph. But that's essentially as much as it can control. It cannot show the degree distribution that the real world graphs represent. It cannot show the community structure that the real world graph has, and it doesn't have the same clustering coefficient. So for instance, for the degree distribution, we can show that it follows a binomial distribution, and the tails go to 0. It doesn't have heavy tails. Therefore, it doesn't follow a basically distribution. It doesn't show nodes that have unusually high degrees. So if we can't basically explain why we have hops in real world graphs, if we start from this model, that means that hops cannot be explained by randomness. So there's something far more complex that needs to explain why we have nodes that are highly connected in the graph. So while we can't really capture things, basically characteristics of the real world graphs using this, still, this is one of the most used algorithms, and the reason for that is that you have one characteristic, you want to see if this is an actual characteristic that, there's some underlying physics behind it. So you essentially model it using a random graph model and see if you can reproduce the same essentially idea there. If you couldn't, that means that you're gonna, look into something else. So still some very good indicator for basically different properties of real world graphs. Now, the second model we're going to look at is configuration model. In configuration model, you're assuming that you're given a set of nodes in the graph, and then you're also given a set of sequence, basically a sequence of degrees corresponding to that nodes in the graph. So we know the nodes, so we know that we have V nodes, and then we know what degrees those have. So let's say that I have a set of degrees d1 through dv, and that's with that constraint, I want to construct a graph. So another way to basically put it is that we can assume that, let's say that I want this graph to have a particular distribution that is desirable, right? So I can just sample the sequence of degrees from that distribution. Let's say that I want degrees to have distribution pk. I can sample from this pk a sequence of degrees and then use configuration model to build a graph, and then that graph is going to have the same degree distribution. So we kind of can control the degree distribution through the graph that you're generating then. So let's say that we want to construct a graph through this approach. First of all, we set let's say that we have V nodes. We select V nodes in that graph. I mean, we basically put V nodes down on the paper, and then I wanted to have some distribution pk. So I sample a sequence of node degrees from distribution pk, and then what I do is that for each node vi, I add di half edges to that node, right? And then in the last step, I randomly choose 2 half edges and connect them to each other. And that's the way you construct these basically graphs using configuration model. So let's look at an example. Let's say that I have 5 nodes here. And what I want to do is to, first of all, sample a sequence of degrees corresponding to different nodes in this graph. And then I say, for instance, node V1 is connected to 3, so it has 3 edges. So I add 3 half edges to node 1, and then this node V5 is not connected, so I don't add any. So let's do that, and this is what it's going to look like. So I have have one node that has degree 3, one node with degree 1, one node with degree 4, one node with degree 2, and one node with degree equal to 0. Now, in the next step, I'm going to randomly sample a pair of these. So let's say that I select this one and this one. And then what I'm going to do is to connect these two to basically stop these two half edges together. And that's going to convert an edge for my graph. Then I go forward, select another pair of edges, and then connect those two. And that's going to transfer another edge in this graph. And I'm going to continue that until I connected everything together. So let's just verify this. This guy has 3 edges connected to it. This guy has 2 edges connected to it. This guy has 1 edge. And this guy has 4 edges connected to it. And this doesn't have any connections. All right. So there are some problems with the configuration model. The downsides include that if the total number of the half edges that I have is not even, then I won't be able to construct my graph, right? Because I can't basically select pairs. There is one is going to left, right? So what we do is that we sample, and then we reject samples that basically we sum all the degrees in that sample, and we see if that's even or odd. If it's odd, you're going to reject that sample degree sequence. So another problem with this approach is that we might encounter self-loops and multi-edges. And as we saw in the previous example, we had self-loop here and multi-edges here. But that's not something that you usually see in real-world graphs. To remedy that, I mean, there's no remedy for that, but essentially as we increase the number of the nodes in graph, the probability of such self-loops and multi-edges significantly basically drops, and it is fine to have a few of them. So it is still fine to use configuration model to generate graphs. But configuration model still has problems to capture, for instance, the community structure that you see in real graphs. Another approach is the stochastic block model. The idea behind stochastic block model is to represent the community structure in the graph. So the idea is that you basically are given a set of nodes. Let's say that I have B nodes, and then we cluster these nodes first into different clusters, and then we set different probabilities for edges connecting different cluster of nodes, right? That way, the generated model is going to show basically a latent community. So to make it official, let's say that I have clusters A1 through A gamma. So I have gamma, essentially different communities. And then I associate to each of these communities a probability of a node belonging to this cluster. So, and all these probabilities should sum to 1. So I say that with a probability of 0.1, you can belong to this cluster. With probability, for example, 0.3, you can belong to the other, and so on and so forth. So, so when you construct your nodes, basically when you construct your graph, you have a set of nodes, and first of all, you go over all the nodes and sample from this categorical distribution to see which basically community this node belongs to. So that's the first step. The second step is that I want to show some basically sense of community. So I want to have different probabilities of edges between nodes within each basically set of cluster, each cluster. and in between different clusters. So I want different edge probabilities intercluster and within cluster. To show that, let's say that I have gamma communities, clusters. I'm gonna have a matrix, probability matrix C, with dimensions gamma by gamma. And each element of these, Cij, shows the probability of having an edge between nodes of community I and community J. So that way, you're going to have different edge density within each community or across different communities. So the generative process for this is that, first of all, you set V nodes to this graph. And then you go over all the nodes and assign each of these to one cluster by sampling from the categorical distribution Pi, P2, P3 to P lambda, right? So that means that let's say that's something like this. So it means that which essentially a probability 0.3 is basically belongs to P1, with probability 0.2 belongs to P2, with probability 0.5 belongs to 0.5. And the way to do this essentially, when you implement it, is to say that, for instance, you set sample a random number from the uniform distribution, basically from 0 to 1, and then we have this spectrum. So essentially, this belongs to P1, this belongs to P2, belongs to P3. So if this value falls between 0 and 0.2, it's going to belong to this cluster P1, cluster A1. If it falls between 0.2 and 0.5, it's going to belong to category 2. And if it's between 0.5 and 1, it belongs to category 3. So you see that basically the length of each of these is proportional to the probability. Sorry, so that's 0.3. Okay, so this has a larger chance for P1. All right, so that's the way to implement it. Now, let's say that I assign different nodes to different clusters, and then what I want to do is that I go select each pair of nodes, Vm and Vn. So this should be A, B, A, M, N. All right, so not IJ. So it says that I will have an edge between nodes Vm and Vn with probability Cij, where basically this corresponds to the probability of having edge between nodes of cluster AI and nodes of cluster AJ. So let's say that, for instance, here we have a set of nodes. The first step, I have 5 clusters. I assign each of these nodes to one of these 5 different clusters. I have this basically kind of structure. And then I say that with some probability, these nodes are connected to each other. With some probability, these nodes are connected to each other. So these are each diagonal terms of that matrix Cij that shows the probability of connectedness within each community. And then we say, for instance, between community, so let's say 1 and 5, there's a particular probability between these two. And the common practice is to have a larger value for the diagonal terms of matrix Cij, so that within each community, basically nodes are more connected, more densely connected. And then at the end of the day, I have something like this, where I see, for instance, here, these are fully connected, so probability was 1 here, and also here. And for this also, all 3 of them are connected. And for this is high, but not 1. And there is, for instance, between these 2 clusters, I only have 2 edges between these 2 clusters here. So it's relatively sparse. Now let's say that what you're going to use this stochastic plot model for. Let's say that I'm developing some algorithm to study the basically community detection algorithm. I have some community detection algorithm, and I want to study this. I want to see if it works numerically. So I generate some sample using stochastic plot model, and I want to see if it can in fact detect the clusters in this random graph. If it can't, it means that my algorithm is not working well. So it is essentially used as test scenario for our algorithms. So while SPM is able to show community structure within the graph, what it can show is different degree distributions throughout the graph. It has different clusters. There is a homogeneous degree distribution within each cluster. The average degree is the same within each cluster. So that's not the case in real world essentially graphs. So that's still a problem with stochastic plot model. So the last model that we want to look at is called Barber-Shelbert. This was developed here at Notre Dame in the 90s. And Barber was a professor in physics, and Albert was his PhD student. So the idea with this is that we don't want to create a graph, a random graph, a real world graph per se. What we want to do is to recreate the process of creating basically a real world graph. So in the previous item, so that means that in the previous basically models, we had a set of nodes, and then we worked on those set of nodes to see the different probabilities of how we connect these, right? How to place our edges. Now, in this approach, we don't start from a set of nodes. We said we only have a few nodes. We don't have all the nodes that we have. And then we iteratively build our graph. This is also called an autoregressive approach. So what we're going to do is that we're going to say that I'm going to skip to the just algorithm, but we can discuss later. So what I'm going to do is that I'm going to say that I have some core set of nodes, and then let's say that n0 number of core nodes, and then I iteratively add new nodes, I call that VT, to these two core nodes. And the way to connect to these core nodes, each iteration is proportional to the degree of the nodes that exist. So that means that if a node is highly connected, there's a better chance that the new node is going to be connected to that highly connected node. That's very similar to the social media, for instance. Let's say that you join Twitter, who are you going to follow? Some unknown, some guy working in a farm in Indiana, or U.S. president. There's a better chance you're going to follow U.S. president than some random guy in Indiana. So that's the main idea. In each iteration, you're going to select a constant number of the edges to connect to. And that constant number should be less than the initial number of the nodes. So that initial number, just to reiterate, should be a complete graph. It means that all the nodes in that first set of nodes should be connected to each other. And then we have a probability. DIT means that the degree of a given node I at iteration t divided by sum of all the degrees in the graph in that iteration. So essentially, that gives the probability corresponding proportional to the degree of that node. So that if we have a new edge between the new node VT and the existing nodes in that graph. So this idea is called rich gets richer, meaning that if you have money, you're gonna get richer than someone that is basically doesn't have anything. So, and the real idea really came from economics. So let's say that in this example, I have two core nodes that are connected to each other. And then I'm gonna, each iteration, I'm gonna add a single node, and I'm gonna basically connect that new node to two of the nodes that already exist in the network. So let's say that I'm adding this new node here. I'm gonna connect it into basically two nodes here, because there were already two nodes, so it connects to both of them. In the next iteration, I add a new node. This is gonna randomly select two of these. All of them have the same degree, so there's the same probability, and it basically selects these two. Now, this time, if I add a node, what I'm gonna have is that I have two nodes that have higher degree. These two nodes have degree 2. So if I add a new node, it's a higher chance, with higher chance it's gonna get connected to these two rather than these two. So I continue that, and I generate something like this. So this idea of autoregressive generative models is something that we're going to explore in our deep graph models as well. So just to summarize, today we studied how we can generate graphs, the idea of generating graphs. So we first wanted to see what we want to generate. We want to generate here today, we want to generate random graphs that represent real-world networks. So for that, we looked what characteristics these real-world graphs have. The characteristics that we reviewed were, for instance, the connectedness of the graph. We looked at the length, average length of the path in that graph. We looked at the degree distribution in the graph. And the last item that we looked at is the clustering coefficient. So next, we look at the models to generate these random graphs. This included Erdős-Rényi model, which was essentially a random graph model, and you're just randomly setting connecting nodes. Then we have configuration model, which is connecting nodes based on a given sequence of degrees corresponding to each node. We have stochastic block model, which corresponds each node to one of the blocks, predefined blocks, and then with a given probability, these basically different nodes of different blocks are connected to each other. And last but not least was the Barber-Shelburne model, which was an autoregressive approach, which was using preferential attachment. At each iteration, it was the new node was connected to existing nodes with a given basically to a given number of existing nodes with a probability proportional to the degree of those nodes. All right, that's it for today. I will see you guys after Thanksgiving. Have a good break.